My name is pronounced Bob Bruner. That's how it's spelled. So anyway, the first half of the talk is basically what the results are, and the second half of the talk is how we get there. If we have to leave some of that out, so be it. The first thing I should say is this is joint work in progress. We hope to finish writing it up this fall. We started in 2008. We abandoned it. Well, we didn't really abandon it so much as just did other things for many years, and then finally came back to it a couple of years ago. Simon's Foundations helped me get to and from Oslo sometimes, and the University of Oslo very kindly hired me on a part-time, one-fifth job for the last 3 years. So I'm very grateful to them for that. And the Newton Institute here is a great setup. It's, everything's worked really well for me so far. So we started doing this because we wanted to calculate the homotopy of some TMF modules whose homology we knew, but whose BP homology we did not. And so we couldn't really use Adams-Novikov or elliptic curve methods to calculate them easily. And so we thought, well, let's try using the ordinary Adams spectral sequence for it. The problem with that was we didn't know enough about how the ordinary Adams spectral sequence for TMF itself behaved to really do what we wanted. So we backed up and started looking at TMF. And we actually managed to finish everything except hidden extensions for TMF, just in terms of TMF itself. But to do the hidden extensions, we actually looked at TMF smashed with the cofiber 2, eta, and nu, and that turned out to actually simplify a lot of stuff. So this is one of the reasons things have taken as long, as now that we know easier ways to do things, we have to rewrite stuff we already wrote. And if you write every section of the paper 5 or 10 different times, it takes a lot longer to write it. So, on the other hand, maybe it's better if you're lucky. And we've worked out this in very great detail. Tools, since we really wanted to do this well, I guess actually a better way to say this is since we're somewhat skeptical people, we actually started by calculating the cohomology of A of 2. And the Davis-Mohold spectral sequence is the method we used for that. There are other approaches. Then once you've got x over A of 2, you could just start calculating away until things appear to be stabilizing and hope you're done. Or what we did was we actually used Grosvenor basis techniques and things to actually turn this into a finite calculation so that we could provably say we are done. So one of the curiosities in the calculation is we don't use any utility brackets. We do use them for heuristic purposes, but we never needed them. We can never do everything with primary information. And one side effect of this is we get a verification of existing calculations with maybe details that haven't been written down before anyway. They probably were there in many people's heads, but now they're on paper.
You verified all earlier results?
You know, I have to confess to not really looking at the earlier results. Sorry. But every once in a while I do, and we've found a few typos, but that's it. But I haven't done a systematic comparison. We should do that at some point. Absolutely right. This is what the answer looks like. Let's see if we can make this a little easier. Actually, let's leave it like this. We'll see it in more detail in a minute. The most notable thing that should stand out to you here is that there is a slope 1/2. Okay, which one's the pointer? If I press the, here, that's it, yes. There's a slope 1/2 line here. And what you see is something that looks very much like KO going up that top edge. And then you see another that looks sort of like a slightly ersatz KO. And another one, 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 and another one. And then the whole thing starts over at dimension 192. Sorry, I forgot to mention prime is 2. Everything's completed at 2. So we have 192 periodicity instead of 576. And at certain points that really simplifies things. Probably we'll want to go back and get rid of that simplification in the end. But the main overall piece of structure here is this is dramatically simpler than x over a of 2. X over a of 2 has this sort of appearance of 4 bands with a huge cloud of things obscuring. And once the differentials have taken place, all that noise is wiped out, and you can see what's really going on here. Just to make a simple analogy, if you think of KO, you've got a z in dimension 0, z in dimension 4, and then you've got a little bit of 2 torsion tagging along. And in the first half, the 2 torsion is there, and in the second half, it's not. In the same way, TMF is made up of these 8 sort of ersatz KOs with a bunch of Bach torsion tagging along. B here, in pi 8 of TMF, we call the Bach class. It's not the Bach class, it's a lift from over the map from TMF to KO of the Bach class, but it maps to the Bach class, and so it makes sense to call it that. The generators of the homotopy that you saw there, first you have the periodicity element we call M for Mahold in pi 192, and that acts freely on the whole thing.
So Bob,
Yes?
so the bot element, what other people call C4?
It will map to C4, yes, right, to be precise. And the rest of the generators fall into 3 classes according to the annihilator of their, the radical of their annihilator over Z adjoint the bot element. So the elements that are not annihilated by Z or the bot element are called DK, BK, and CK in each of the k equals 0 through 7 copies of KO there. DK is in the 0 stem, BK is the sort of new bot element in the kth copy of KO that happens in the 8 stem, and CK is in the 12 stem. Then the etas in one dimension above the bottom have annihilator 2, exactly 2. The bot element acts freely on them. And then all the rest of the elements have annihilator whose radical is generated by 2 and B. And they, let's see if I have to think a bit about this. I think all of the annihilator ideals lie between 2B and its cube. And there are various annihilator ideals in between. Okay, so those are the elements we call nu K, epsilon, nu K in the 3 stem, familiar element probably. Epsilon K in the 8 stem, again, should be familiar to everyone. Kappa K in the 14 stem, everybody knows and loves kappa.
So you're talking about the infinity term, or you're talking about
This
the
is
homotopy?
homotopy.
Why is nu annihilated by 2?
The radical of
The radical,
its annihilator ideal is 2.
I see. Okay.
If we look at the various nus, some of them will be annihilated by 2, and some of them will be annihilated by 4, and some by 8. And then kappa bar in the 20 stem. Turns out we only need 1 kappa bar, but in fact, most of these aren't defined for most K. DK, BK, and CK are defined for all of them. The new Ks are defined for all K, 0 through 7. The rest of them are only defined for some values. So let's be a little more precise. First of all, the first family, the 0th KO.
We don't have any elements that we call 116 modulo 24?
No generators.
So are these multiplicative generators, or?
Yes, that's what I mean, as a ring, generators as a ring, sorry. And we'll see the charts in just a little bit, which is the easiest way to see where the elements lie. If you take the unit from the sphere into TMF, then 1 eta nu, epsilon kappa, and kappa bar all go to the elements we call 1 eta nu, D0, eta 0, nu 0, epsilon 0, kappa 0, and kappa 0 bar. So they deserve either name, and we'll leave off the 0 as a result. The map from TMF to KO sends D0, B0, and C0 to the generators of KO star in degrees 0, 8, and 12. In degree 4, the map is isomorphism in every degree before. And in degree 4, TMF star is 0 and KO star is Z. And in case kappa and kappa bar aren't as familiar to you as eta and nu, let me just say how I think of them. The relationship between the bot element and kappa bar is exactly the same as the relationship between 2 and eta, or the relationship between eta and nu. That is, it's given by a Frobenius operation. In a co-bar construction, you simply take the co-bar description of the element and square every entry.
But kappa bar comes from the sphere, and there you have no B.
Well, so it's, yeah, exactly. It's not in the image of this.
But how am I
of
supposed
this
to interpret his Frobenius then?
In X over you aren't. You're supposed to interpret it in TMF. So in TMF, we see more structure to kappa bar than you would see in the sphere. That's an interesting point. Epsilon, we'll see something interesting about epsilon, sort of stepping in to do the job that the bot element wasn't there to do in a minute. And then kappa itself is just the square root of bot times kappa bar. So it's just a little quadratic extension of what you'd expected to see. So here's the chart that shows that in some detail for you. Here is bot times kappa bar. It also is epsilon times kappa bar. So this is why this element's there in the sphere, even though the bot element's not, because epsilon is there in the sphere. So epsilon kappa bar exists in the sphere, but in TMF, bot times kappa bar and epsilon times kappa bar, both this element in the 28 stem, which is the square of the kappa in the 14 stem there. So to me, this bot, kappa, and kappa bar all sort of come as a group, and if you kind of take those three elements, take the ideal generated by those three elements, and then look at its powers, it's an interesting array of elements in the homotopy of TMF here. Let's see, what else did I want to tell you about this? Well, just sort of where things are, and where eta and nu are. In this little sort of picture at the beginning here, we're going to see over and over and over again. This is very familiar to everybody, probably. Yes, here. Nu cubed is actually just eta epsilon, because sigma is gone. In the sphere, nu cubed is eta squared sigma plus eta epsilon, but here it's just eta epsilon. And yes, the other thing is, what is the notation? Solid vertical lines are multiplication by 2. Solid diagonal, 45-degree diagonal lines are multiplication by eta. If they're black, they're mapping to bot torsion-free elements, and if they're red, the target is bot torsion class. If they're dashed, as over here, this goes one stem to the right, so that's an eta multiplication. If it's dashed, it means it's hidden in the atom spectral sequence, in the infinity term of the atom spectral sequence, but it's true in homotopy. So this is a picture of the homotopy, but I'm using E infinity of the atom spectral sequence as a kind of skeleton to hang on. But the actual relations in homotopy are being displayed here, not just E infinity. So you see, that's not what I'm supposed to do. You see, for example, a new multiplication from eta 1 here in the 25 stem up to the 28 stem. And so this little eta squared, eta cubed is 4 nu that you see in the first KO turns into a slightly different picture in the second KO. And notice the first two, you have the eta and the eta squared, those are bot torsion free. Those just, as soon as you get up to 8 stem, this looks very much like a copy of KO if you don't look closely enough. But over here, this is clearly, we'll see in a minute a little bit more about this. I'll skip that for now. Let's see, so the other piece of notation, the dotted, since we use dashed lines for new multiplications for detected by H2 in the atom spectral sequence, I chose to use dotted lines to indicate hidden new multiplications that aren't detected by H2 in the atom spectral sequence. So this is the first, so this is the part that Paul would simply draw on the board for you right off the bat, but at least up to 24 here in this. as he said, this is the part you can draw by hand, and that's why I'm using slides. I wouldn't want to stop there. It's a lot more interesting stuff going. Okay, so that's, anyway, the first bit of this. And, yes, now, I said most of the other generators besides B, C, D, and nu don't exist for all K, and this gives a precise description of them. The B, C, D, and K, you can see, so what the chart means is it starts in degree 24K that's the left column, and then you add 0, 8, 12, 1, 3, 8, 14, or 20 to that to get the stem this element lies in. And so you have D's, B's, and C's for everything. You've only got eta 1, and eta 4. You've got nu 2. Nu 3 is in the picture. It's actually equal to eta 1 cubed. It's not maybe, well, not too much of a surprise. So you don't really need it to generate pi star or TMF, but it's very useful to have that notation for general formulas. And then nu 4, nu 5, nu 6, you do need. Nu 7 is actually 0. But again, it's useful to have nu 7 in general formulas. Also, this kappa 4 bar is actually kappa bar times d4. So you don't really need it to generate, but again, it's nice to have it in general formulas. So those are the, if you eliminate the ones that have parentheses around them, it's a minimal set of generators for the homotopy of TMF. And then this, I've arranged them here in families, the nus, the epsilons, the kappas, and the kappa bars. For a very specific reason, and that we can explain best by talking about modular forms. The map from TMF star to the ring of modular forms does not hit the discriminant. But there is an element which would have mapped to the discriminant, given that it's a multiplicative map, had at earlier terms of the spectral sequence. Now, in the Adams-Novikov spectral sequence, it's already true at E2. In Adams spectral sequence, it's not true at E2 of the Adams spectral sequence, but such an element exists in the spectral sequences like Davis-Mohold or May, or, well, yeah, let's stop there, which converge to E2 of the Adams spectral sequence. So what that means is in the Adams-Novikov spectral sequence, delta is gone at E3, and we have a total bracket at E3 that can that multiplication by delta computes. In the Adams spectral sequence, it's already gone at E2. So there's this bracket really two brackets here that we can compute at E2, which correspond to multiplying by delta. And this differential on delta actually hits nu kappa bar, and that's hitting H2G, and that's why this is the form of the bracket that calculates, what tells you what multiplication by delta accomplishes. As with all Massey product, by the way, when I say total bracket, I often mean Massey product, or maybe I mean total bracket. To me, total bracket is a composition, and Massey product is a DGA. But of course, you can just look at the DGA of self-maps, and then everything is a product. So the distinction's not that important, but I compute these things by computing homotopies of chain maps typically. So I think of them as total brackets because I think of them in composition terms rather than DGA sort of terms. That's why but in my, yes, I did say Massey products in the slide though, because I had a chance of thinking about it. Yeah, so anyway, delta here is only defined if G annihilates X. Delta prime is only defined if H2 annihilates X, and they're going to have different indeterminacies, of course. If you take delta and apply it to the classes that persist into modular forms, they behave quite regularly, although the indices in this first row are quite interesting. The generators of the KOs in the 24K stem get off to a kind of a slow start. In the 0th one, you got the generator right there at the beginning, and bot times it generates pi 8. In the next one, bot times the generator in 24 only generates 8 times pi 32. And that's that index 8 here. So if I start with 8 times the generator in degree 0 and then apply delta to it, I will get the generator in degree 24. In fact, delta is not defined on 4D or D, so we have to start up at 8D. And you can see that D2 is going to be index 4, 8 dimensions higher when you multiply by the bottom half, because 8 over 2 is 4. And so you can see this pattern of 1, 8, 4, 8, 2, 8, 4, 8, 1, etc. And when you get to the periodicity element, you're back to where you started, so multiply by n. The C6 classes, or 2 C6 classes, are much more regular. They just, it's smooth sailing. There's no sort of peculiar divisibility going on at all. Here's where the bot element and epsilon come in very interesting fashion. Bot and epsilon are both acted on non-trivially by kappa bar. So you can't apply delta to the bot map or to epsilon, but their sum is killed by kappa bar, so you can apply delta to that, and when you do, you get B1 plus epsilon 1. Same story there. When you apply delta to that, you get B2, B3, and then you hit B4 plus epsilon 4, B5 plus epsilon 5, and then B6, B7, and then this is a mistake, sorry, I typoed there, it should be B plus epsilon comes in. Yeah. Darn. Okay, so oh well, one typo. Yeah, so in a way this says one of the things about what epsilon is doing for you here. When you multiply these things by 8, then it becomes very, very regular. That erases this little bit of noise, and 8B1 goes to 8B2, etc. It behaves just like the C's. So 8 times the bot maps behave quite regularly. When you look at these guys in X, this is how you calculate them. You start with, well, let's see, what is this chart? This is that famous picture I started with pointing out over and over again at the beginning. We have eta squared, eta cubed, and then you can divide by 2 and divide by 2 again. And eta on the left, detected by h1, you multiply by h1 again, you got h1 squared. Multiply by h1 again, you got h1 cubed, but that's then h naught squared h2. And starting on this side, start with h2, h naught h2, h naught squared h2. So these sort of converge to the center here. And now we apply, delta prime. Delta is not defined on these guys, but delta prime is. So that's why we need both of these toe brackets. So if you compute delta prime on the eta family, it just takes each one to the next. So H1 will detect eta, gamma detects eta 1, H1W2 detects eta. Well, it would have been eta 2 if eta 2 survived. This doesn't survive. Similarly, eta 3 doesn't exist. Here's eta 4 though, and then none of the rest of these will survive the spectral sequence. But when we compute delta prime, I've also been quite careful here to record the fact that this actually has indeterminacy. So this is the precise calculation. It's not just sort of, well, you figure out how big the set is. And then over on this side, it's interesting. Delta prime is defined on the classes detecting H2, but it is defined on the class of detecting 2H2. I put these out here just to H2 squared is non-zero. So, I'm sorry, I don't know if that was why you were frowning. Maybe you were frowning for some other reason. But we can apply delta prime once we get up to 2H2 here. And then when we throw away the elements that don't survive the spectral sequence, this is what's left. So you see the eta family, eta 1, and then nothing again except for eta 4. But when we multiply two of these, we got eta squared, delta prime of that's eta 1, delta prime of that's eta 1 squared. Then that's the end of the story for a moment, and then eta 4, and eta 1, eta 4 pick up. So these are all sort of avatars of eta squared in these different KOs that come along. The 0th row here is in the 0th KO. The first row is in the first KO. Second KO, third KO, fourth, fifth, sixth, seventh. Notice this is all gone. Well, that's sort of like with KO itself, between 4 and 8, it's all 0. There's no torsion sitting there. So this torsion is gone by the time you get to the last of the KOs here. And then on this side, of course, the news, you can't do this, but then 2 nu, all of these exist, except this one. This is nu 801 cubed, that was actually nu 3. So you have nu, which is equal to nu 0, nu 1 actually is more like 2 nu 2. Here's one of the places where we departed from Enriquez's notation. He calls this something decorated with, I think, parentheses perhaps, 2 nu delta 1, I think. We grappled with whether we wanted to do that or not, and it was just too ugly. We could not bring ourselves to do it. And so we finally decided, damn it, this thing's indecomposable. We're just going to write it as nu 2 and accept the fact that it behaves differently. And it turns out it's had nice benefits in terms of the description of the duality in the homotopy when you get to the self-duality of the B torsion here. So anyway, you have this two-adic pattern of the nus. You have nu, and then nu 1 is actually delta prime of 2 nu. Nu 2 is then back to the bottom. Nu 3 is up here in the middle. It's 4 times. It's delta prime of 4 times the previous guy. And then so you have 1, 2, 1, 4, 1, 2, 1, and then I'm not sure what to say in the last row, so I'll stop. At any rate, that two-adic pattern is the same as the two-adic pattern you see in the way, actually, it's dual to the two-adic pattern you see in the way the decays sit inside the decay multiplied by the body element. And these nus are actually behaving quite differently from the rest of the torsion in homotopy. If we let gamma b be the b power torsion here, there are a couple of general things we can say about this. So that's gamma b of TMF star is the elements that are annihilated by sufficiently large powers of b. So usual notation. And nu epsilon, kappa, and kappa bar elements are b power torsion. The rest of the elements are not. We saw that when I defined them, I guess. The other thing is, here's another interesting thing about epsilon. Bx equals epsilon x whenever x is b power torsion. So this is sort of, epsilon is some kind of a sort of echo or reflection of the bot map that sort of acts on the torsion side of things. As a general principle, the multiplicative relations among all these elements are extraordinarily simple. In general, if you take an xi and a yj, you could profitably write that as parenthesis xy sub I plus j. And that's pretty much true with very few exceptions. The exceptions come from the variant to divisibility of the nus. Okay, so this, that's not surprising because you're multiplying by some power of delta. You multiply by delta to the I here, delta to the j here. Of course you multiply by delta to the I plus j. Remember that was at E2, or maybe even a spectral sequence converging to E2. And there are lots of interesting things that can happen along the way. So that's not a proof of anything. It's just a heuristic that suggests what the answer ought to be. And the answer is that, so it's a good heuristic.
Except for some exceptions.
Well, yes, very good. Thank you. So here's what happens with the nus. This is kind of fun. Nu 1 nu k is twice nu k plus 1 for 1 and 5, and it's 0 otherwise. Nu 2 nu even k is nu even k plus 2. And that actually, if we back up slightly and think about the way the spectral sequence works, we have a Z8 cross of ambiguity in our choice of choice of nu here. It generates a Z8, and we can pick they would all be detected by the same element in the atom spectral sequence. And we use these first two formulas, nu2 squared is nu 4, and nu2 nu 4 is nu 6, to choose a precise nu 4. That eliminates the ambiguity in the choice of nu 4. Similar to this, eliminates the ambiguity in the choice of nu 6. And then it follows that nu2 nu 6 is nu squared m automatically. Here's a general notation. When you see a subscript that's larger, that's 8 or larger, just subtract 8 for it and multiply by m. And that's a convenient heuristic, well, not heuristic, it's a definition. Here's another interesting one that comes out of this. Nu 4 nu 6 is either plus or minus nu 2m. I suggest it should be plus, and that's how we choose the sign of m, because there's a z cross of ambiguity in the choice of m. It's basically a phenomenological talk, so I'm just sort of describing what this stuff looks like. So here's the first KO here, and it's very much like a KO. Once you get up to here, actually it's not so bad down here, although you get this little extra stuff hanging around it. And by the time you get out to here and up, it doesn't even have that torsion hanging around, V torsion to confuse you. The one thing you may notice is this generator in degree 4, above the 4 up from the bot map, is in the wrong Adams filtration. So if you look at the Adams spectral sequence for the map from TMF star to KO star, it's 0 in that stem. And however, if you look at the one exact sequence given by those two and the third term, it's easy to prove that it maps isomorphically in homotopy, even though it's 0 at E infinity. And then I would suggest, I guess one of the things I want to convince you is that you should become familiar with these elements and like them as much as you like eta in KO. And so we're all happy to have, Z, Z2, Z2, 0, Z, 0, 0, 0, Z in our lives. And I think these elements ought to be just as familiar and sort of, well, okay. I'm not convincing you yet. Okay, let's see if I can do better. So this is the next one. This is even more fun. Yes, please. At any point.
You said something about the choices of M having to do with units in Z. Is Z Z2?
Yeah.
There's more units.
They won't show up. There's an integral version to this where you get rid of that choice. Okay, so here what you see is that the KO it gets off to a bit of a slow start. By the time you get up to here, the generator is there, but it's got an epsilon accompanying it. And epsilon is still hanging around here, but finally when you get up here, it's all alone and it behaves normally, except you multiply by 2, you see what you expect, multiply by 2 again, and then you have an Adams filtration jump. So this is another way in which these are quite ersatz versions of KO. So you have this this little KO running up here with the hidden 2 extension up here and the hidden eta extension. And then sitting in this epsilon here, well, so lots of things are happening. I mean, there's, first of all, the eta 1 here actually supports a new multiplication, which is different from the etas that you've seen before. But that's the way it behaves. But of course that goes away. It's hitting a bot torsion element. It's still here. But this, well, no, it's gone already at this stage. And it's gone it's gone very quickly. There are lots of interesting homotopy relations here, and I put in names that are supposed to be as informative as possible. You can read off tons of relations from these. For example, if you look at this guy in the 35 stem, you can see that it's eta kappa kappa bar, but it's also nu B1, it's nu epsilon 1. And so anyway, these slides will be somewhere if you want to sit down and look at them more carefully. In the second one, this behavior of nu 2 starts to get kind of interesting. It supports quite a lot of non-trivial stuff. For example, nu times it is non-zero, nu squared times it is non-zero, nu cubed times it is non-zero. So nu cubed, nu 2, that's actually the longest multiplication of nus you can get. 4 nus in a row. Can be non-zero, but 5 in a row will be 0.
I'm really glad to see that 801 capital bar squared.
Ah, yes, yes, exactly.
That was the key element in Armina's thesis.
Very good. And we did read these, so. Yes, very good. Here also the generator in the beginning of the KO is index 2 in the stable version here. So you have a hidden extension getting from V2 up to, I'm sorry, index 4. I make that mistake every time. When you see this jump, you think you're talking index 2. The reason this label BD2 is here is to prevent that error. The name of this element that's unlabeled here is too ugly. You don't want to see it. The best name for it is 2B2. And that's what you should call it. Its name in the atom spectral sequence is a little messy.
Let's go back to,
Yeah.
as long as I've interrupted you already.
Yeah.
This class 801 kappa bar,
Mhm.
that may or may not have lots of robust properties. Can you name it in the atom spectral sequence?
Yeah,
For the
it's
sphere?
gamma D naught. Oh, no, it's not in the sphere that I know. I don't
It may not
know.
be a sphere, but is it,
It may be in the image from the sphere, I don't
Is
know
it-
for sure.
whatever is H whatever's in 15 cubed? Could it be that element?
Yeah, that's good. I should look at that.
It might actually be a really robust element.
Yep.
All right.
It, actually, this epsilon 1 here is probably a class that you're familiar with. You know the class Q
Yeah.
in homotopy of spheres. That matches epsilon 1
I
here.
guess I'm sort of asking what the Hurewitz image is. Can you read that?
We've made some progress on that, but we haven't actually done it quite systematically. We've figured out a bunch of them. Okay, so then 48 looks like this. You see, 801 kappa bar squared and other friendly elements. 72. This is starting to remind you of the upper end of KO. Clears out quite a lot. There's down here. There's your nu 3. Notice this nu is always there. If you go over 3 and up 3, you see that nu always sitting there, divisible by more or fewer elements and supporting more or fewer multiplications. That's always there. Let's see, kappa bar to the 4, that turns out to be interesting. That actually introduces a tiny bit of ambiguity in the definition of V3. But there's very little Bott torsion here. And then the next one, we start over, this is halfway through the cycle. And now things are starting to get a lot like the beginning of the process. And let's see, here's this kappa 4, it's indecomposable. Kappa 4 bar is decomposable, but it's convenient to call it that.
What's 801 kappa bar?
801 kappa bar. It's just,
It's non-zero.
yeah, it's just sitting back here.
It's that same guy, right?
Yeah, the guy we were just talking about.
Okay.
And then the next time around, this looks a little bit like the second one, the fifth one. The fifth one and the 1th one, or the first one, it feels odd to call it the first, but then if there's a 0, so I guess it's okay. We're in Britain, it's okay. Ground floor 1 is up off the ground, it's excellent.
So why is kappa bar to the 6th? Why is kappa bar to the 6th 0 in this picture?
Where's kappa bar to the 6th?
Why is it 0 in this picture?
It's killed by, I don't remember. It will be killed, however, and kappa bar to the 5th.
This has got all these relations on it, right? So
Yeah. So let's see. where
kappa
are
bar to
we
the
here?
5th is one slide back.
That's why I can't find it. Yes, there we go. Yes, exactly. Yes, divisible by a heck of a lot. Here's another very interesting one. Nu squared, nu 4. This is not properly speaking how you indicate hidden extensions in atom spectral sequences. Properly speaking, the hidden extension goes from nu 4 to eta epsilon 4. Because multiplication by H2 does not take, is 0, but it's detected in the atom spectral sequence by the bottom of these two elements. But that's one of the reasons I said this is not E infinity, it's homotopy, using E infinity as a skeleton to hang it on. So I prefer, I've had some arguments about whether this is a fair notation, but I like this notation because it encapsulates this relation neatly. This is a bit like the way nu cubed in the sphere is a sum. Now, let's see. That one we've looked at a tiny bit. Now, this is the fun one. This is great fun. This is A to 1 to the 6th here. That's the highest power of etas. That's the end of the story for the etas. A to 1 to the 4th is the only 4th power, or the only element in the 4th power of the ideal generated by the etas. A to 1 to the 5th and A to 1 to the 6th are the only elements. Then 5th and 6th, and then A to 1 to the 7th will be 0. But notice you got almost an entire, two eta. Well, you got eta cubed and nu on this is of order 8. Nu 6 is of order 8 here. In detecting the hidden extensions, once we know that this hidden extension is here, everything else falls. So this is, you can get this one fairly easily from a slightly higher up, and then everything else just follows by the multiplicative structure. So it's good to start at the top and work down.
What filtration is A1 to the 6th?
It's in 31. That's the index over on the left. That doesn't make sense.
It's not divisible by 6.
It's not divisible by 6. It's possible I actually typed something wrong when I made this chart. Let's see, 2, 3. Excuse me. This is homotopy. Gamma to the 6th is 0. I mean, gamma to the 6th isn't there.
So there's been a filtration.
There's been a filtration shift, yes. Yeah. It is in filtration 31, but it's a hidden extension.
Which was the hidden extension that told you everything?
I'm trying to remember which one we did first, but something, come back here. Something between the nu 6 and the A to 1 to the 6th. We've done this so many times in so many different ways, trying to make it more efficient, that I think what we did was we first got the 2's here, and we knew the nu because that's actually an x, and that then forced an eta cubed, and that forced a nu, and that forced another nu, and that just led everything out. They all sort of fall away then. Okay.
It's almost Talmudic, right?
Yeah, it is almost, you're right, that's a good analogy. But now this is the clean one, right? This is the last of the KOs, and there's no bot torsion. And it looks almost like a copy of KO just starting here and going up, except whoops, that's not where it starts. It starts down here, and again, as usual, it's slow to get started. It's off by index 8 in the 0 stem, and the 8 and the 8 squared aren't there until 8 dimensions later. All right, so now here's what the duality looks like. This is all familiar stuff, so I hope you don't mind me racing through it. M mod x infinity, you just take the cofiber of M to M adjoin 1 over x. You can do this in either homotopy or algebra. In spectra or algebra. You can iterate that to do M mod x infinity, y infinity, and you have this nice little exact sequence relating these guys. Now, why do I say this is a short exact sequence? No idea. Okay, we'll pretend I didn't say that.
No, it's immediate from the definition.
Oh, good, thank you.
M goes to M1 over x, generates a long exact sequence, that's it.
It does generate a long exact sequence. Why is it short?
Short exact.
Yeah, but you've taken the kernel of the next.
Of course, thank you. Exactly, that's, yes. Here's the mod x infinity and the gamma construction in homotopy, here and here. That's kernel, that's co-kernel and kernel. And then here in the middle, we have the homotopy. Thank you. Good to have an audience that knows what you're talking about, in case you don't. Anyway, here's the duality theorem expressed in these terms. If we took John's gamma maximal ideal of TMF this would be a suspension 23 over here in Brown Commonness dual, or a suspension 22 in Anderson dual. They're all saying the same thing. The question is whether you want to take the co-fiber or the fiber, but they carry the same information. Personally, I like the fiber because it's close. It has a multiplication, but we wrote this up in terms of the co-fiber, and I didn't have time to rewrite all of this. So, and anyway, there's time's running short. Now, how do we prove the duality? Well, with all this information about the homotopy, it's straightforward. You take the basic block, which is what you would get by killing off M, call that N star. It's generated in dimensions less than or equal to 180. Its B torsion is 0 outside the range 3 to 164. Remember where the red stuff was. When you take N star bound B infinity, then that C7 over B generates the top class, and it gives you a Z. And then if you just take the multiplication map here, you get a Z of BM isomorphism from N star tensor Z of M to pi star TMF. And then the M torsion, of course, is M power torsion in the homotopy is 0. And so that means then that N star tensor Z of M mod M infinity is the homotopy of pi star TMF mod M infinity. And then you get a nice little short exact sequence that says basically you only need to understand what happens to B infinity, that is N star mod B infinity and gamma B of N star, in order to understand what happens for gamma of B and M, or mod B infinity, M infinity. So that means now you can compute what pi star of TMF mod B infinity and M infinity is, and that's all in degrees. So now we take 192 away from 170, and we get 172, sorry, and we get minus 20, and there's that C7 over B, but now divided by M as well. That's the top class in here, and it's from the calculation, you can see it's 0 in the degree before, so you have a short exact sequence here expressing, sorry, what's that? Yes, right, let's find what we're talking about. Yes, there we go. Pi star TMF mod, the whole ideal, 2 B and M. Sits in this little short exact sequence, and you can see where its top degree is and and that it's a Z2 infinity there. So then when you take a Pointryagin dual, the homotopy is concentrated in degrees 20 and up, and you have 2 adducts in degree 20, so you take a homotopy class realizing that, and then take the TMF module map that generates to give you a map from sigma 20 of TMF into it. And then a simple argument using the fact that TMF smash the double of A of 1, or the complex whose cohomology is the double of A of 1, is BB2, allows you to prove this map that you've written down as actually an equivalence. So that's the proof, the calculation proof for the duality. That equivalence of spectra you get there gives you isomorphisms with different shifts on different layers of the homotopy, as usual. You expect 0th, 1st, 2nd, etc. local cohomology to shift by different amounts. And the most beautiful one is the one down inside this delta here. This is essentially the B torsion, except leaving off the new classes. And you'll see in a minute why leaving off the new classes is a good idea. Then we also call KO sub bracket K the Z of B submodule generated by the DBs and Cs, together with the etas that exist in that version. So eta and eta squared, eta 1 and eta times it. Then in the next one, eta 1 squared is sort of in the first 8 degrees, but eta B2 is not until the second one. So when you take KO2 mod B infinity, it looks a little different. And they all have slightly different character. You can read those off the charts I gave you quite easily. When you take the B torsion mod this delta, then that of course gives you just the news. And if you take pi star mod the B torsion, that gives you just these KOs. So this part of the structure is easily described. Gamma B mod gamma 2, I don't have time to do because it turns out the time is running along pretty fast. class, and I didn't actually have time to make slides for it either. But this is the most beautiful picture, so maybe this is a good flip. I'm glad I got to this. The deltas are inside the boxes. The nus are not in the deltas, but they're here to sort of show you how things behave. Now, the top one's delta 0 and the bottom's delta 6. The degrees in the top one are going from left to right. The degrees in the bottom are going from right to left. So kappa nu 6 here is dual to eta epsilon up there. And you can see that if you multiply kappa nu 6 by eta, it's non-zero in the same way that eta epsilon can be divided by eta. So multiplication by eta here corresponds to division here and vice versa. And that's the expression of the duality here. So you see a perfect duality between these. Yeah, okay. Yes. So there's a nice example here. This kappa nu 6 and eta epsilon. The way that works is the vast majority of these is that x is dual to y in the sense that when you pair them, you get the top class in the Q mod z is comes from expressing x and y in the notation where I said write the elements out and then put all the I plus j's at the right. Okay, it should be eta epsilon nu kappa and with total index 6. So you see kappa nu 6 there, dual to eta epsilon. There we have an eta 0, an epsilon 0, a kappa 0, and a nu 6. And this expresses 2/3 or 3/4 of the duality. There's one other pattern like this that expresses the rest of it. One other thing is, we all know that spectra are better than homotopy groups, or especially when you filter them like this. Down here, you don't see anything interesting about nu here, but over here you see that this class really was divisible by nu in a way that isn't apparent over here. So this is reflecting hidden extensions in the exact sequences that you get. Or not hidden extensions, but extensions, so that when you look at B infinity here and gamma B there, then when you look in the middle and lift an element back here, it's actually multiplied by something. You see a non-zero relation there that comes from the previous stage. Delta 1, delta 5, perfectly dual. You see exactly, so this actually means to memorize those 8 pictures I showed you, you actually don't have to. Just memorize 4 of them. Memorize the right 4. And then delta 2 and delta 4. And then finally, delta 3 is self-dual. And here's the other pattern. There you see eta 1 squared kappa bar squared is dual to kappa bar to the 4th. And in every case, the product of the two is eta 1 squared kappa bar to the 6th. And then these nu 3's hanging out to the 2 sides. Now, here's the other interesting thing about the duality. These nus are exactly dual to the fact that d times dk has a non-trivial index in the subgroup generated by dk. And so there's this upside down duality here, which says, I didn't write this out. Oh yes, there it is, yeah. Yeah, the nu 7 minus k has, its order is exactly the index of dk and bk. Yeah, okay, so I hope you know what I mean. Take dk, multiply with a bot map, it's some multiple of bk. That's index is exactly the order of the dual nu at the other end of the picture. This, actually, I could have gone from k equals 0 to 6 and k equal 1 to 7, because the 2 of the summands are 0, but it's true the way I wrote it, so it's okay. Okay, well, this is fairly familiar stuff from previous calculations. So Hopkins, Bauer, Douglas, Francis, Enriquez, Hill, and Conter have all made contributions to the understanding this point of view, the modular forms point of view. And these modular forms C4 and C6 and delta are corresponding to the elements that generate the Z's in here. So the map, well, first of all, the kernel of the map to modular forms is exactly the 2 torsion. Second, BKs are basically the C4s. The CKs are 2 C6 delta Ks. The DKs are this 2-adic pattern times the delta Ks. And this is all 2 complete. We actually wrote down the answers without 2 completion. They're quite a bit messier. Chose not to say that today. This map to modular forms together with the Adams representative at E2 completely determines these elements with 3 exceptions. C2, there's a mod 2 ambiguity here. There's a class order 2. You could add to it without changing its image in modular forms or without changing the Adams representative. Same for B3 and C6. And I kind of thought I would only have time for the homotopy and not for how we do this. So maybe I'll just tell you that. Davis-Moulton spectral sequence, a lovely spectral sequence which allows you to do something like the Cartan-Eisenberg spectral sequence, but with a non-normal subalgebra. What you need for that is a little bit of extra structure. What you need is that the quotient should be a coalgebra as a gamma comodule, or dually. The co-tensor product could be an algebra. And then you need to write down a nice resolution. When you do, this turns out to be the resolution you would use to resolve an exterior algebra on 3 generators. Beautiful multiplicative resolution, easy to calculate. Turns out E2 equals E infinity. And the terms are KO, KSP, and then Adams covers of KU with the class in degree 2 killed off. If you took KU and tried to kill off that class in degree 2 as a KU module, you'd just get a split. You'd have an HZ and another KU. But here, over KO, it doesn't split. So, sorry, you have these guys here. And the key differentials come from elements in homotopy in the 22 stem, the 28 stem, and then those are the 2 things, basically. The hidden extension, well, I won't say any more about that. Enough, thanks.
Questions?
I noted down a relation, which I think I've seen at the very beginning of your talk. I just want to check whether I've misread that or not. You claimed at some point that kappa squared is kappa bar B.
Yes. That's D naught squared is GW1 in the spectral sequence.
It seems very strange to me, but we'll tell that.
Well, it comes from the fact that bot class times a bot torsion element is the same as epsilon times a bot torsion element. Actually, this goes back to Mimura. But it's often stated as kappa squared is epsilon kappa bar.
That I would be happy with.
Yeah, but bot kappa bar and epsilon kappa bar agree.
So if your B corresponds to C4, your B1 or B0 corresponds to C4, then that would be an algebraic relation in the descent spectral sequence for the homomorphic exponent, and this relation is not true.
Ah,
So there's something funny going on with interpretation of elements, I think.
oh, that's interesting. Let's talk about that. Okay, so here bot times kappa bar has to be bot torsion because kappa bar is. And
I have no objection to that.
in X for A of 2, there's the relation D naught squared is GW1. D naught squared detects kappa squared, and GW1 detects bot kappa bar. kappa bar is G, bots W1. So the kappa bar squared is B kappa bar is certainly true just from A of 2, plus the fact that you're talking about elements of order 2 and there are no more elements of order 2 in there. So it's the only element it could be if you have a non-zero element of order 2 and it's detected in the atom spectral sequence.
Take that one off. Alright, so just for the record, did you actually check it with Tillman-Bauer's charts and make sure you got the same answers?
In places. We actually want to do this systematically rather than,
Alright, and now to settle a bit in the audience, what's your longest differential in the atom spectral sequence?
yes,
Just the
this is
number,
the lovely
just the
thing.
number.
4.
4.
There's a single geometric D3, which is the E naught kills C naught W1. And that has to come from eta squared kappa equals 0, which comes from Toto.
So you have nothing longer than a D4 in the atom space.
Yes, and then that implies a D4, which implies a D2, and E5 is E infinity.
Alright, who won? Let's take it off. Alright, we'll reconvene in half an hour.
Were you competing for shortest or
No,
longest?
they had an open order on the differential.
I think that's